Good afternoon. My name is Owen Sayre from ARO3090's Team 9. Today we will be presenting about a planetary mission to Neptune's moon Triton. Here's an overview of the members on our team, including Owen Sayre, myself, Nicholas Witucki, and Freddy Hernandez. Here's an overview of what we will cover in today's presentation, including a mission overview, both graphical and technical, an introduction, modeling and assumptions, technical calculations and MATLAB analysis, a final design with the selected architecture, a summary, and additional details in our appendix. We'll begin our mission overview by defining a high-level overview of the mission, and then observing each of 3 defined mission segments in detail along with technical calculations. This slide has a brief overview of our mission goals, including our main goal to travel to Neptune's moon, Triton, performing 1 planetary flyby, and some restrictions on mass, launch window, total time, and launch C3. The main objective of our mission to Triton is to design an interplanetary ballistic trajectory from Earth to Neptune to allow a spacecraft to perform deep scientific study of Triton. This is a graphical overview of our mission plan, including a planetary flyby, arrival on Neptune, and then a transfer into an orbit around Triton. We've separated our planned mission design into 3 distinct segments, highlighting the different stages of our journey that our spacecraft will take. The first stage is from Earth to Jupiter, including the spacecraft's exit from the atmosphere, as well as a flyby maneuver about Jupiter. This will result in an angle change to optimize segment 2. And in the second segment, the spacecraft takes a ballistic trajectory to approach Neptune and will enter a parking orbit around the planet. In the last segment, a prograde burn will alter the Neptune parking orbit into an elliptical shape, which will intersect with Triton's orbit. A Hohmann transfer will allow the spacecraft to enter a science orbit around Triton and conduct scientific studies of the moon. This slide highlights the main objectives of our planned mission, including the launch window, transfer time, mass restrictions, launch C3, and trajectory minimums. The overall mission objective today is to perform a deep study of Neptune's moon Triton by using an interplanetary ballistic trajectory from Earth to Neptune. This slide highlights the main software that we used for analysis in this project, including NASA's Horizon and MATLAB, which we use specifically for pork chop plots as well as interplanetary transfers, and developing our own tools for analysis. The analysis that we conducted in this project relates to each of the 3 defined mission segments. We've separated our mission into comparing mission architecture to determine the optimal plan for our spacecraft to take. Throughout the duration of this project, we made several critical assumptions, including the location of Jupiter, Neptune, and Triton, assuming constant gravity, and we also used patched conic approximation for our orbit determinations. For our calculations specifically, we used several theories, including patched conic Hohmann transfers, pork chop plots, and Lambert calculations for interplanetary transfers. We also defined several physical constants, including the mu value of the different planets along with their radii. Using an SLS function with only block 2 values, we've determined that we have a mass of 1,500 kilograms, which is equal to 1.65 tons. And with that, we have a maximum C3 value of 117.5 kilometers squared per second squared, and anything lower than that will also work. The mission vehicle that we've selected to complete this project is the New Horizons spacecraft, which was originally launched in 2006 and reached Pluto in 2015. Because of that, we know that the spacecraft is also capable of reaching our goal, which is nearby to Neptune. Now, our goal window is from June 2029 to June 2023, and our mission period is approximately 15 years long. We have some other specifications listed here, and the rocket would end up being 3 stages. The launch vehicle we've selected for the New Horizons spacecraft is the Atlas V, which has a lot of mass and a lot of carrying capability.
Stage 1, Earth to Jupiter.
Before considering realistic mission designs, we wanted to highlight an alternative approach, which is called doing something completely wrong. Now, with this method in mind, we decided to do a direct Hohmann transfer from Earth straight to Neptune. This resulted in a massive C3 of 167.5, which meant this was entirely not viable for us. Going based off of our mistakes, we decided that doing a flyby maneuver would be more beneficial for us. It would increase our delta V while also allowing us to still complete the mission within a 15-year timeline. We developed 2 architectures to compare. The only differences between those 2 were the launch C3. Architecture A has a much larger launch C3 of 115, while Architecture B has one of only 95.
Here on our first transfer from Earth to Jupiter in Arc A, we have a C3 of 115 on takeoff from Earth, and an arrival C3 of 184. We decided to choose a launch date 10 days before our pork chop plots have 0, and our time of flight is a total of 515 days. For our Earth to Jupiter arrival on Arc B, we decided to start out with a C3 of 95 kilometers squared per second squared and ended with 107.1 on our arrival to Jupiter. And we decided to keep our launch date on January 27th, 2030, and we had a total time of flight of 592 days, which is slightly more than before. Here are the pork chop calculations for our Arc A with the C3 of 109.2. And for Architecture B, we have the same exact calculation. Here's our first interplanetary transfer from Earth to Jupiter in Arc A. And we have a C3 of 110.6, which is more accurate than the pork chop plot. Here for our Arc B, we have a completely accurate V infinity of 10.35 when we arrive on Jupiter. Here for Arc A, we have a departure C3 of 110.6 and an arrival C3 of 175.5. And for Arc B, we have a more accurate 95 C3 and 107.1 C3 for arrival.
For Architecture A, we decided to put the learn by doing philosophy to the test, and we made yet another mistake. We made some hand calculations to determine the trajectory change, or bend angle, due to the flyby of Jupiter, and we got a completely inaccurate result. And so we sought to create a tool that would instead use MATLAB to determine if the spacecraft would successfully fly by the planet. After inputting the arrival and departure vectors into the program we made, we can determine if the flyby would be successful. As long as the radius of flyby is larger than the radius of the planet, we will not crash into the planet's surface. Using the MATLAB tool, we can see that Architecture 1 does not successfully complete the flyby. This means that it barreled straight into the surface of Jupiter, while Architecture 2 has a radius, a periapsis, turn angle, and aiming radius highlighted, which means it was a successful flyby. In addition, we would like to highlight the additional delta V gained with Architecture 2 as our approach aligns with the planet's rotation. This will help us later.
Stage 2, Jupiter to Neptune. And here for the second transfer of Arc A, both departure and arrival have the same C3 of 184. The second transfer in Arc B has a more accurate C3 of 107.1 and an arrival C3 of 231.8. For Arc A, we have a completely incorrect C3 of 22.1. For Arc B, we also have a C3 of 22.1.
For Architecture A, the time of flight for the second interplanetary transfer is about 2,700 days, while the velocity of arrival is about 18.3 kilometers per second.
And for Arc B, we have a time of flight of about 300 days greater than Arc A, and we have a lower V infinity. For Arc A, in our interplanetary calculations, we calculated that we have a C3 in departure of 175.5 and an arrival of 334.8. And for Arc B, we have a departure C3 of 107.1 and an arrival C3 of 231.8.
Wow. Architectures A and B are initially very similar. On departure, the C3 is only slightly different, but ultimately, that magnifies the change between them. The time of flight between them is different by about 300 days, which ultimately could allow for additional science, exploration, or orbital maneuvers and positional correction. Based on this, we've decided to ultimately continue with Architecture B for selection.
The third transfer, Neptune to Triton. Our calculations from Neptune to Triton have a delta V of 11.37 on entry and an aiming radius of 579,717.9 kilometers.
On the left, we have a simulation of our proposed ecliptical orbit around Triton, originating from Neptune. And on the right, we have an elliptical orbit around Triton itself. We initially enter a retrograde orbit around Neptune. This reduces our velocity so that we can enter a prograde orbit around Triton. We have an elliptical orbit and we capture Triton's orbit.
And this is with respect to the previous simulations.
Here's a summary of everything we've done today. As you can see, we've prepared extensively for this presentation, and we hope that you've enjoyed watching and listening to this. After developing all of our different codes and making sure that our trajectory plan would fulfill every goal we set out to make, we were ultimately able to fulfill every goal outlined for this project. Thank you so much for watching. Have a good one.